500 and by Swedish standards, and they have 6,000.
Right.
Which doesn't look good to me, right?
Yeah, that's true.
On the other hand, people can basically continue to do what they used to do, which is fine. But if people die, I don't know. It doesn't sound too good to me.
Yeah.
But you know, 6,000 and by is a lot. It's a big number.
Yeah, that's quite a lot. Given the number of people there living there, it's quite a lot.
So how is India dealing with this?
Well, death rate is still, it's not much. I mean, given our population, you know, it's a huge population.
That's right. But you have a young population.
Yeah, that's true. Yeah, we have young population, but even the, you know, older people, they are also quite a lot.
So maybe you are simply more healthy than the rest of us, which is good.
Actually, we don't know. I mean, nobody knows what is the correlation, and things are happening, but we have to just accept it. So I don't think any scientific evidence is there that what is the particular reason for this.
I mean, you're just lucky that it seems to affect you less than say in Europe or in the US.
Yeah, that's true. Yeah. So yeah, that's the reality, and we are happy that less people are dying. So that's a good news.
Yeah, I mean that's really the sad part. I mean,
yeah.
A colleague of mine he in Oslo. I mean, he had retired some years ago, and he was 85 something, but he died from corona.
Oh, that's sad to know.
So this is it can happen, right?
Yeah, that's the saddest part. Yeah. I mean, otherwise, if it is like a common flu that you are down for a week and then it's okay, I mean, nobody will actually worry about all this, right?
Yeah, that's right. That's right.
Yeah. So maybe we go online. Okay.
Yeah.
So is it already we are online?
We are we are already online now. Participants can enter.
Okay. So Helga will start in 3 minutes.
Okay, perfect.
Yeah.
I'll start in 3 minutes.
So there is actually an Indian postdoc in NTNU now. Did you meet this guy?
Yes, I met him.
Okay.
He's a very nice guy. I think he just left quite recently. I think he's going to, of course, there could be more than one Indian, but in my group working with Espen Jacobsen.
Yeah, that's the one. Yeah.
Yeah, you know, I think he left quite recently for, where did he go? Somewhere in Europe for another postdoc term.
Oh, I see.
And he was a very nice guy.
I see.
Clever person. So I guess he's basically traveling around looking for a permanent position somewhere, which is not easy to get.
Yeah, given current circumstances, I mean, it's not that good situation. Yeah.
Yeah, no, this is just difficult for everyone, and particularly for young people without jobs.
Yeah. Okay, so we start now. So welcome everybody. It is my honor and privilege to introduce our speaker today, Professor Helge Holden. Professor Holden is a professor of mathematics at Norwegian University of Science and Technology, Trondheim, Norway. He was the chair of the Niels Henrik Abel Board from 2010 to 14, president of the Royal Norwegian Society of Sciences and Letters from 2014 to 16, and currently he is the Secretary General of International Mathematical Union. His research interests are in partial differential equations, mathematical physics, stochastic analysis, and flow in porous media. He has several fundamental works in this field. He has published more than 170 research publications, including several highly cited publications in prestigious journals. So today, he is going to talk about ellipsis metric for the Camassa-Holm equation. So let us welcome Professor Holden, and it's over to you, Helge, now.
Thank you very much, Ujval, and thank you very much for giving me the opportunity to talk about this. So I'm very happy to be given the possibility to talk to this audience in India. It would be very hard for me in regular days, in regular period to come to India. So this is great for me, and I will talk about something that has been of my interest for many years, namely the Camassa-Holm equation, and I will talk about a new Lipschitz metric for the equation. And this is joint work with Jose Carrillo in Oxford and Catherine Grunert here in Trondheim. And the paper has been published very recently and it's open access, so you can actually download the paper. It's a long paper though, but it's freely available on the web. So let's talk about the Camassa-Holm equation. I will not assume any familiarity with the equation. So here is how it looks. So it is first order in time. It has this mixed space-time derivative. It has this constant kappa. It's a convective term. It has nonlinear transport. It has nonlinear diffusion and nonlinear dispersion. And we are interested in the initial value problem. So we are given initial data and we want to look at this equation. It was derived by Camassa and Holm in an amazing paper in 1993, where they derived some of the main properties of the equation. They sort of identified most of the interesting properties, but they didn't provide the detailed mathematical proofs, mostly derivations, but no proofs. So there is a lot of work to be done. And this equation has turned out to be very popular. I think there are more than 1,000 papers on this equation on MathSciNet. So it has been widely studied. So why has it been studied? It doesn't look too pretty. I mean, it's just these 2's and 3's and minuses and pluses. It does not look very pretty, but it has these properties. So it was derived in the context of water waves, and it can also be used as a model for hyperelastic rods. Now the derivation for water waves is a little bit contested, but still it is considered as a model for water waves by many people. More interesting is that it's completely integrable, so there is a lax pair and you can do the inverse scattering transform. However, that is much more complicated for this equation, say, compared to the KdV equation, for which it's well studied and well understood. It's bi-Hamiltonian, so there are two underlying Hamiltonians from which you can derive the equation. It has also what is called algebra geometric solutions, and there's an infinite hierarchy of integrable equations, of which this one is the simplest. So you can just imagine what the higher order equations look like. They are just rather messy. One can do that, and I've done that, but I will not discuss that at all here. There are infinitely many conserved quantities that somehow goes together with this being completely integrable. Will not play a big role today. It has some very nice solutions that look like solitons for the KdV. They are called peakons in the context of Camassa-Holm. We will see a lot to them. It can be extended into systems and multi-dimension, which is a little bit strange because it is rather rigid. As I mean, you can't change this minus into plus, or you can't change 2 into 3 then. all these properties that I've listed will disappear, but you can, if you are very careful, extend it to a system in space or in as a more unknowns than just the U. We will not do that, however. We will focus a lot on the wave breaking in finite time. Steep gradients, while the Sobolev norm remains finite. We will study that a lot. So let's talk about the kappa that appeared on the previous slide, this number. So what's the role of the kappa? The problem with the kappa is that you need this to be positive if you want to work with this equation in the water wave setting. However, the majority of papers have no kappa being equal to 0. So there is a way to get rid of the kappa. So if you solve the Camassa-Holm with a positive kappa and you introduce V given by this expression, so you mix space and time here, but more importantly, you add the kappa here, then we will solve the equation without any kappa. Now, so if you're periodic, say, if U is periodic, then this you can play with or without the kappa as you please. But if you are on the full line, it changes the decay properties. And the key thing is that the only explicit decaying solutions, in particular these peakons that I talked about, can be computed when kappa vanishes. So that's one of the reasons why kappa being equal to 0 is the most popular case. I mean, we have studied in the general setting where the asymptotics of the U can be different from 0, and in particular also different from plus or minus infinity. We studied in 2 papers what happens then. But I will do kappa equal to 0 here. So let's do some of the classical results here. The first paper, and this was a very, very important and instrumental paper, was a paper by Konstantin and Escher in ACTA in '98, where they actually proved a rigorous proof of that the equation had wave breaking. So in finite time, the solution developed singularities, and it was not clear how to go beyond the wave breaking. Sort of the next step came slightly thereafter, and this is a typical one of many results. So if you look at initial data in H1 and you look at the quantity U minus UXX on the initial data, and if that is a non-negative function or a measure, then you have a global solution for all time. It's a setup here for any finite time. You can compute the unique global solution. What happens, so if this quantity here is no longer with a sign, so if this becomes negative, what happens then? Well, there are many results, variants of what happens then. So if you take initial data that are odd with a negative derivative at the origin and slightly more smoother, then one can show that the solution can only exist up to a finite time. After that, there will be the solution will develop singularities. And then came some years after that, a completely different approach by Bressan and Konstantin, and myself and Renaud, where we looked at well-posedness in completely different variables. So I talk about conservative and dissipative solutions. We will return to that. But this was with a completely different technique with using a change of variables. The other results mostly relied on the Kato approach to construct solutions. So we did a different method that will play a role today. So there are many ways to rewrite the equation. I mean, nobody works with the equation in the ugly form that I had on my first slide. So one way is to introduce this U minus UXX and call it M, and then the equation has this form. That's a nice equation, and many people like to work with that. Another is to write it in U, and this now looks like Berger's equation with a pressure term, so it looks like an 1D Euler. But in this case, P is given by this equation, which you can invert. Invert it and then put this into here, but then it becomes a non-local term. So mostly it's displayed in this form. The form that we will work with is related to the one I had here. It's a Berger thing plus a pressure term. But we also need to look at the measure mu that satisfies this equation in a weak form. And P is given by the same expression that we had with the big P, but where we introduce a measure that is essentially the H1 density. We will return to that in detail. So this is the form that we will work with. And now we look at functions that are in H1. Mu will be a non-negative radon measure with the absolute continuous part being equal to u squared plus ux squared, so the H1 density. So this is very important that the measure, as soon as it's absolutely continuous, has to have this form. And this is a form that I will work with today. So the goal of the talk is to determine a metric with this property. So if I have, with the alpha starting at 1, so if I have two conservative solutions here, I want to take the metric, the distance between the two functions like this, should be bounded by the initial value of the same quantity. So that's what we want. There are some different results by Bressan and Fonte from 2005 and from Grunert, myself, and Renault in later with different approaches and different metrics. The problem is that the usual Sobolev spaces, H whatever, and LP will not work. You have to do something more tailor-made for the equation. Okay, so what's the problem here? Well, that's most easily displayed in the multi-peakon case. So there is a question in the chat here. I don't know if I should look at this. Okay, that's for you, more for me. Okay, so the multi-peakons. So we define the Hamiltonian. We have two vectors, P and Q, with n components, and we form this Hamiltonian. We form the dynamics based on this Hamiltonian in the traditional way. And if we write out the H, we will get these two equations. So what's the relationship with the Camassa-Holm? Well, that comes here. So if I form this sum, the U down here will be a weak solution of the Camassa-Holm equation. And you see it's a weak solution because of the absolute value here. So it's a weak in contrast to the solitons for the KdV, which are infinitely differentiable. This one will not be differentiable at all. But still, it's a weak solution. Okay, and you can see here as n equals 2, and the two p's have the same sign. So you see the faster the peakon it is, the bigger it is, the faster it goes. So it overtakes the smaller one and sheds all its mass onto the small one, which becomes big and moves apart. That's the dynamics. The peaks never coincide, and you can see the peaks are coming from the absolute value. So this looks pretty nice. So what's the problem? The problem is the following. So if I do opposite p's and I do the symmetric case, the peakon and peakon will collide, and at some particular time, namely this time here, it's all gone. U equals 0. And that's a bad thing, because you come from non-zero data and suddenly you have 0. And then you would think, so how to continue beyond that? This is a wave breaking, and the question is how to continue past that. One solution is obviously just to continue with 0, but you feel that cannot be the whole story. So in the two-peakon case, you can actually analyze this. So you can see that the derivative becomes negative infinity. U becomes 0 almost everywhere. You can see a small piece in the middle where it goes a little bit up and down, but it's 0 almost everywhere. But the Sobolev norm remains finite. This is in contrast to the wave-breaking formation of shocks with conservation laws. It's quite different. So here there is a problem, and this is the source of all the problems. So the characteristics, if we look at the characteristics from the previous example, they look like this. At the time where the solution became 0, all the characteristics are vertical, and at the tip of this, the value 0 is sitting. So it's not constant along the characteristics as it is in the conservation law, but they all come together. So of course it's tempting just to continue them vertically with 0 value. if you look at the H1 density, u squared plus ux squared, 5 units away from wave breaking, the mass is concentrated at these 2 peaks. 2 units before wave breaking, it's getting closer to the 0. 1 unit away becomes very close, and at the wave breaking, it goes into a spike like this. So it's pretty clear what happens here, and this corresponds to the measure then. And the absolutely continuous part is the H1 density. Namely, what is clear is that this will approach a delta function. So it seems that the mass is going from the absolutely continuous part into delta function. And then, of course, delta function, if you look at it pointwise, is invisible. So what happens here? Uniqueness and stability goes down the drain because suddenly the whole thing vanished, but you feel it shouldn't really just continue to vanish. So what we do is that we encode the energy into the measure, and we will carry that along to keep track of the energy so we are not losing it. So another possibility is clearly to reflect the characteristics with respect to this horizontal line. And then you get this, and of course you can do the computations and 0, but then it comes out at something. And we would like to pick up this one. But we need a mechanism to separate this from the 0 one. So this is what we will call the conservative solution that we will study today. There is all immediate. It's not that straightforward, but it turns out that one can keep a fraction of the energy, what we call alpha dissipative. So it's a fraction given by alpha that is kept. The rest is thrown away. But you cannot do this randomly because you need to keep keep whatever function as solution of the equation. And if you do 2 dramatic changes in the t direction, it will no longer be a solution. And we did this in a paper in some years ago. But I will not go into that at all. I will study conservative solutions here. So we will play a little bit formally with the quantities involved and derive a set of new equations for which we can study this. So I introduce somewhat randomly, but there is a reason for this. But it takes some time to describe it, so I will be short on that. So we define the accumulated energy up to a certain point x, and that's the f. And then I need to modify phi f into a g. I need a function that is strictly monotone. I cannot be sure that f is strictly monotone. I need to modify it in a careful way to get a strictly monotone function, and this is my g. Then I introduce the inverse called strict y of g. It's a generalized inverse. A problem that with this function g is that its domain, its range will, the domain of y, the range of g, will depend on the energy. And so we will return to that issue. This is a technical thing. So formally, y, strict y is the inverse of g. So I can write it like this. I can differentiate, and I will get this differential equation for strict y. There is an s here that you haven't seen before, and you will not see it. It's a complicated expression that I will not display. A strict u is a velocity along this curve. You may ask, so is the y a characteristic? In some sense it is, and we will see exactly in what sense slightly later. So I need, so I recall that the script y is given by this and with this equation. Now I want to derive the equation for script u, the velocity. Again, I assume everything is smooth, so I just differentiate like crazy. And I get this one. The left-hand side, you see, is exactly the same for script y and script u. The right-hand side will be different. Q, I will display what Q is. It's px inserted script y. And script p is p inserted y, script y. Then I also need an equation for p, And it looks like this. Again, the left-hand side is always the same. The right-hand side is more and more messy. And the R and the S are explicit and computable, but they are just messy, so I will not display them. So I have this new system of equations, these three equations. And now I derive them under the assumption that everything was smooth. And one can do this in terms of weak solution and get the same equation. This is technically rather complicated, but the result is not too surprising that the equations are the same, even in the general case of weak solutions. But so as I said, I mean, the problem is that some of these equations have domain that depends on the energy, and that's messy because we want to compare two solutions that may come with different energy. So we have to scale them away. So I take the script y tilde with is a scaled U, and C is the total mass, the H1 norm squared of U. And the name of the game is to try to estimate the time development, and I want to determine it in terms of two solutions and in terms of differences here. And you see they always, with the scaling, they always live on the same domain. So y, u, and p. For technical reasons, it's better to work with the one square or the square root of p, and the difference in energies as well. So this we need to estimate this. So you just take the solution and then compute the time evolution of the L2 norm. What is nice, and I do not stress this too much in the talk, is that the solution of this system will suffer no singularities at all. So we transformed it into new variables for which there is no singularity. It just passes through this point where everything goes a little bit out of whack, but it doesn't see it. In these variables, everything is smooth. So that's the big advantage, and that's the reason why we do it. So there is an alternative way that was studied before we came with our approach, that is transforming it into what we call Lagrangian variables. And I will show some of what went into this and why this has some difficulties compared to the present approach. So we are given initial data, U0 and the measure mu0. We introduce Lagrangian variables, so y should correspond to the characteristics, h should correspond to the energy, and u should correspond to the Lagrangian velocity. So this is how I set it up initially. And f0 is just integrated energy. Then one can show, and again it's a calculation similar to the previous one, that it satisfies this system of equations. So here is the characteristics, and here is the development of the velocity and the Lagrangian velocity, and here's the development of the energy. Again, this system has no singularities. We have been able to transform it into a system for which all the singularities have disappeared, which is nice. And here you can see the relationship between the characteristics and the script y. It's at the bottom here. So the script y is the characteristics y, but with a different tag, particle tag. We change a little bit around on it. So there is a relationship between the two, but it's indirect. Okay, so if we play with the Lagrangian variables, I call big X and the three independent or dependent variables put together in a vector, and I just write the time evolution as S sub t. So, okay, here comes the figure. So out here we have the Eulerian, the original variables, U0 and mu0, and here we're into the Lagrangian variable. So the initial data transformed into a point here. And we let time run, and we move along this curve and out here. The problem, and then we can go back. We can go back from this back, and this will be the solution of our problem. The problem with the Lagrangian variables is the non-uniqueness of this transformation from Euler to Lagrange here. The different points here that correspond to the same solution in U and mu. So this, we can recover the measure, that's just a technical thing, in this way. And the problem is, as I said, the lack of uniqueness, and this we call it relabeling. There are many ways to label particles here. So if I have two solutions over here that are very close, they may correspond to a solution here or a solution here. And if they are close on the Eulerian side, they should be close on the Lagrangian side. But this means that I have to pick a particular Lagrangian representative. And that's not so easy to do in a natural way, so that I can compare two different solutions. So this went into the setting of relabeling, which is rather complicated, and we avoid that in the present approach. So the metric is easy to define. The distance between two solutions is just the sum of the L2 differences, like this, of all the variables, including the energy. So we just need to look at the time dynamics of this. And the theorem that we eventually prove is that we have this Lipschitz property that the distance is controlled by the initial distance. There is an exponential factor in front, but it starts at least with a 1 equal to 0. So it goes like this. And it also has the property that when the energy disappears, it goes down to 0. Okay, so we have this scaled system of equations, which is, I have to say, I was not too pleased when we were forced to do this, because, so I think I have it here. So here's the scaling. Here's the scaling. I had to scale this to get the same domain. And A is the square root of the energy. So there's a square root of the energy outside. These are the equations. It's not too attractive to compare two solutions when you see that you have downstairs a to the power 6, which is a quantity you want a difference between two of them. But that's the price you pay. Well, we have to live with it. So I will look at one estimate. I mean, it's becoming more and more complicated, so I will look at the simplest. So the setting is the following. So we have two solutions of the script y equation. It looks like this. It still has some complexities with this divide by the energy here. And we want to look at the difference between two. And I jumped ahead here. So the left-hand side is the L2 difference of two solutions. And I want to take the time development. And I just do it in the regular way. So I get the difference between the two time derivatives. And here I insert the equation. So I get this here, and I get this term. So the first one is the term from the right-hand side, and plus this, the various terms from the left-hand side. So these are the three terms I need to compute. And I call them I1 to I3. These are each of these terms. And I will go through at least some of them. Not all of them, but some of them. So this is the way you would start. So I took the first one, which I called I1, which is the difference in the y's and the difference in the u's. And I want to estimate in terms of the sum of the two differences. And that's straightforward. You know, you get the sum of the squares, and that's simply equal to the sum of the squares of the L2 norm. So that was easy. But it's becoming more difficult. So this is the I2. I still have the difference in y's, but I got these terms here. And now I want to compare this. I don't want any derivatives here with respect to eta. And I want to take a difference between the u's and the energies. But they are all convolved into some mess here. Okay, so what do? I do the following. I have to split it up. I mean, this, I split it up. This looks like a mess, but if you look at the inner part, I need to take the difference between these two quantities. I can write it as the sum of these two terms, where I separate out the biggest of the a's. I mean, it's not a difficult estimate to show, but and this is what we get. So at least we get some control. We get the difference in the energies here, but we still have terms that we do not like here. So I do the following. So I take the last term here. That's the same term we had already. That's this term here. So I take this term with the maximum here and split it into these three terms. So I look at this term here with the difference in the power u third power here, and I split it up into this, and then I can factor here, and this looks good. This term looks like a mess because it's a difference in the eta derivatives that I'm not too pleased with. These terms also have eta derivatives, but in a more controlled manner. If I could get just this term combined with this term, I would be happy. So let's see how it goes. So I have some inequalities that are quite useful. One can show that if I take u squared times the y sub eta, this is bounded by the energy. And it comes in handy. So if I look at the J2 term, which contains this, this sum here, plus this sum, times the difference. I want to take this difference together with the difference here. That would be good. Now I know that for the first term, I know that u1 is the biggest. Then I replace in this term u2 by u1. That gives me u1. I get the u1 squared together with this one, and that I can bound by this. Here there is a typo. This should be a u2. Here I know that u2 is biggest, so I replace this one by u2, and I take this u2 together with the u2 here, and then I can again use this. So I need to separate out what is bigger and what is smaller in order to be able to use this thing here. Otherwise it will just be a mess. So that's what happened. I got the 2 here, and I got the 2 here, and I get the u2s separate and the u1 separate here. And now I can estimate this by 8 to the 5 and this by 8 to the 5, and that cancels this guy over here. And I can use the standard trick to get the sum of the squares. So then comes this one, which was a hassle for a long time because we get the difference between the derivatives. So there is one natural way to look at this, and that's to integrate. And I will do that. So I integrate here, so I get the square here, and then I get this term, and minus the derivative on this term, which is a term that is a little bit messy. Fortunately, one can deal with this. This term drops because eta equal to 0 and eta equal to infinity 1 corresponds to spatial x at plus minus infinity, so it drops because of decay. So I'm left with this quantity here, and so that's what is written here. And it turns out that one can bound this. One can bound this by the L infinity of this, and again times 8 to the 4. And again, this cancels that one, and I can get the difference in the L2 norms. So this means that for the first equation, I was able to at least give you an indication of how one can obtain this this estimate here. At least I showed some of the estimates involved, and there are many of them, and they somehow go along similar lines. Right, and one can do similar for the other equations. That is an understatement. it took a lot of work, and it was not that easy to get all these estimates. But eventually it all came together. You somehow get you gain some practice. So this means that yeah, you gain some experience with the practice, and then you do the sum of the L2 norms, and that will give us this, and eventually it will give us this estimate. Now I will go back to the two-peakon example and show you explicitly what these functions look like in the two-peakon example, because it's somehow you can compute all these quantities in this particular case. It boils down to one particular ODE that either you can solve it explicitly or you cannot, and it turns out that with some change of variables you can indeed do it, but it's not a priori obvious that you can. So this is how it looks in Eulerian variables. It's an exponential, a linear combination of exponentials, with the alpha, beta, and gamma given by this, and the gamma here is where the peak is. So the gamma follows the peak. But you see, it's complicated, but you can easily imagine that the differential equation involving these quantities will not be solvable explicitly, and E is the total energy. So remember that U look like this. It becomes negative infinity, the derivative here, becomes more and more vertical, while the peak gets closer to the origin, and eventually it all becomes zero, and then it pops out on the other side. If we compute the G, that was the sum of the energy and some other quantity. This is a strictly increasing function. It's not constant here, but it goes exponentially towards a constant. It becomes vertical exactly here, or rather exactly here. It becomes more and more vertical, and here at the wave breaking is exactly vertical. And here's the explicit expression, where alpha, beta, and gamma are on the previous slide, and you have the hyperbolic singe given as is, you can see here, and exactly at the peak, these two functions, the minus gamma and the gamma, become zero. So this drops out, and it jumps from e squared half to 3e squared half here, and that's the jump we see here. And the script y, which is the inverse of g, so you can just flip the x and the y axis. So when g is vertical, y becomes horizontal, so here is exactly horizontal. And the scaled, I mean, scaling makes a big difference when you work with the functions, but when you graph them, the scaling doesn't make a big difference. It looks basically the same. It is quite different. So it is strictly increasing here, and then it becomes constant for a certain interval, and then it becomes strictly increasing again. And here's the expression. The log of something divided by, and then the inverse singe. And if you look at the function itself, so the script u, this is in fact, it's a little bit surprising. So the upshot of the change of variable is that script u becomes linear. So it's piecewise linear. This function is linear. It's linear, it's linear here. Becomes the peaks go towards the horizontal axis like this, and suddenly becomes horizontal, so constant equal to 0, and then it pops out. But this is much less dramatic. There is no derivative becoming infinity here. It just drops slowly down to 0. And the scale function, as I said, the scale function is not really very different from the other one. And here we can see in the variable eta, it's linear. However, the dynamics of the peaks, I mean, it's governed by the constant or these functions, so t in a complicated manner. But for fixed t, it's a linear function, piecewise linear function. And this was the u. And you see the u is much more dramatic. So we're able to transform it into more benign variables. So let's recall the two-peakon example here. Goes like this, becomes horizontal and pops out. And this is a variable that we are interested in. So I'm approaching the end here. I like to display this dynamics here of a four-peakon. So you have 3 spikes going. We know these spikes are going to the right. We have these, what's called the anti-peakon, going to the left. And if we look at these are the peaks. So here it seems that the peak is just reflected like this and thrown back. It looks like this one is thrown back and it hits another one and is thrown back. And the same with the third one, and the fourth one is just reflected off once and goes back like this. If you look at the video, we get a different impression here. Because here it certainly looks like the negative peakon passes through the 3 positive ones. But if you look in the center of characteristic, it seems that they're reflected back like this. So I guess it's a matter of language rather than mathematics, whether you prefer the description on the dynamics on the right, left, or on the right. Okay, so I think I will stop here, and thank you very much for your attention.
Okay, thank you, Helge, for this wonderful talk. So I think we have a couple of questions here. Can you see, for example, Helge, in your screen, question and answer section?
Oh, yes, yes, I can see it. So the first question is, can one extend this to other dispersive equations like KdV and Hunter-Saxton? This is a very interesting question. So to the Hunter-Saxton, yes, it can be done, and it has been done, and we did that as a warm-up to the Camassa-Holm, because Hunter-Saxton is so much simpler. So we did that. So that there is a paper giving the exact same results for the Hunter-Saxton, with the same authors. So you can just look it up. Whether one can do this for KdV, we haven't looked at this. And in some sense, it's not necessary to do the same thing for the KdV, because KdV starts smooth and stays smooth. There is no wave breaking for KdV. So I don't know if there is a need to do this transformation. And because you could do the transformations directly, because as I said, the solution is smooth. But I think you have stability in regular Sobolev norms, so I wouldn't go this path for the KdV. So then this is another question from the same person. Can we use this to construct numerical schemes? This is another very interesting and very good question. Yes, I think can one derive numerical schemes for this? There are different numerical schemes for the Camassa-Holm equations. Some based on geometric methods, and some based on finite difference. And it's rather subtle. I mean, this is one of the few equations for which you can write down a natural difference scheme. You do the computation, and out comes a non-physical solution. That does not happen with many other equations. It is so, but you have to be careful, and then if you do it in a careful way, you can get the convergent numerical method. This could provide an alternative. This could indeed provide an alternative, because you have sort of insisted on staying conservative. You have a smooth solution. You would think that basically any method would work. Then you have to transform back into the original variables, the little u, the little p, and the mu. But I think that can be done. We haven't done it, but I think that's something one can do, and it would be worthwhile to do it. And it would have the advantage that you would know that you would get the conservative solution out. While if you do a different scheme with the Camassa-Holm, it's easy to end up with a dissipative solution, because a different scheme will have, by default, built into it some dissipation. So it's harder to get a different scheme that goes to the conservative solution. So they are very good questions. Excellent.
Okay, so thank you, Helge. So I request participants to write their question in question and answer box if there is any question. So I have one simple question, Helge. So you talked about these two different types of solutions, dissipative and conservative.
Yes.
So which one is physical? I mean, I don't know what physical means here, but do you see any difference?
Yeah, this many people ask this question, and I've asked myself this question as well, and it's not clear, because in the water wave situation, I think the equation is so artificial. That's my point of view, that it's not easy to see what happens in your tank in your lab if you set up to derive the waves according to Camassa-Holm. My guess is that you would have the conservative solution, but there's always some dissipation that it maybe not be encoded in the equation that you use, that eventually will make the waves die out. But that may not be a fact of the Camassa-Holm. I don't know. I don't know, Ujval. I mean, this is difficult. It depends on the physical setting.
Okay, thank you, Helge. So if there is no more questions, so let us thank Professor Helge Holden again for this wonderful talk. So thank you, Helge.
Thanks a lot, Ujval. Thanks a lot to all of you listening. I enjoyed it.
Yeah, so just before closing this session, I have a small announcement. So our next speaker on Thursday is Professor Lagrangian, and he's going to talk about nonlinear boundary value problems in connection with harmonic functions. So see you all on Thursday. Thank you, Helge. Bye.
Thanks a lot, Ujval.
Thank you. Bye-bye.